Okay, we probably should start just to be on time. Is it all right, Levin, if we start? Would you like to? So we continue our seizure prediction workshop with the morning session on database and contest development today. Before I introduce our first speaker, I'd like to make a couple of announcements. Please visit our sponsors, and also there are still places available for buy breakfast tomorrow morning. You can register via conference website, or you can come to the registration desk and people will help you to register as well. I'd like to promise the audience that speakers will be on time. As the speakers go over time, I will move closer and closer to their personal space. So I'd like to ask all speakers to be on time. We have 15 minutes talk and 5 minutes discussions between the talks. So our first speaker for today is Benjamin Brinkmann from Mayo Clinic. And Benjamin will talk about seizure prediction algorithm development and validation by Kaggle. I'm delighted to introduce the first speaker because last year's seizure detection contest was won by a young Australian Michael Hill. So thank you, Benjamin.
Thank you. Thank you. Good morning, everyone. I'm going to be talking about the seizure prediction contest that we ran last year on Kaggle.com. We also ran a seizure detection contest before the prediction contest, but if you have questions about that, please catch me afterwards. So the reason we tried to approach these problems through this sort of online forum on Kaggle.com, just these difficult technical problems requiring some very specialized machine learning skills, which are in very high demand right now, very expensive sometimes to bring in people to a research group. So we thought we would try to see if we could leverage this very active and very good machine learning community in a very cost-effective way. And the other goal of this contest, which has been a big goal of our laboratory and our collaboration with Brian Litt's group at Penn in developing the IEEG portal, is trying to promote reproducible research through data sharing, through algorithm sharing, and open source solutions. For those of you who aren't familiar with Kaggle.com, it has a very unique format. It's a completely online experience with forums and different competitions some are posted by universities, some by corporations looking for solutions to different problems. The way it works is you provide the data, they host it on their site, contestants download the data, they work with the data, and then they upload a spreadsheet full of classifications. There's a real-time feedback in this leaderboard format. So immediately when they submit a classification, they get some idea of how they did. And it's a very engaging format. There's a lot of back and forth, a lot of cooperation between contestants. For this competition, the contestants could use any signal processing or machine learning method that they wanted to. It just had to be, the classification had to be done by an algorithm, not an epileptologist sitting there marking or scoring or anything like that. And this problem, as I know many of you know, is particularly challenging from an algorithm perspective for a number of reasons. First of all, the data imbalance problem is just tremendous. If someone has one seizure a month, you're talking about like a 10,000 to 1 ratio of interictal time to ictal time or pre-ictal time. And that's challenging for many classifiers. And then, given that if you have even a small false positive rate in your algorithm, that can still add up to a lot of actual false positives over these long spans of time. There's quite a bit of intersubject variation. In fact, we've got a paper that just came out in PLOS One on analyzing the dogs, but showing just a high degree of intersubject variability in all of the features that we looked at, and even the timing of the pre-ictal period. So you have to do some type of adaptive or subject-specific approach. A big limitation has been the data, availability of data. Lots of work has been done in the past on patient EMU records. These are good. These are oftentimes the best we have, but they're not necessarily optimal. These are 10 days in duration on the outside. You may have seizures clustering. The patients are being tapered off of medications. It's not necessarily optimal for algorithm development. And then, of course, the big difficulty, which I know we've all kind of talked about over these series of meetings, the seizure prediction conferences, just benchmarking algorithms, comparing algorithms directly. It's hard to do a head-to-head comparison on the same data. Just in very broad strokes, the machine learning approach to seizure prediction. At the center of it is a machine learning algorithm, an algorithm that learns from the data. You train the algorithm or teach it what you're looking for by providing it with labeled training data, preferably from multiple subjects over long periods of time. You extract from that data features, which could be spectral features, correlation, anything you can compute from the data, basically. Once the algorithm is trained, then you're able to feed new data using those same features, those same computations into the algorithm, and it'll classify the data. The data that we used for this contest was from the NeuroVista system implanted in 8 dogs with naturally occurring epilepsy. We had, the data was amazing. We had a few dogs with over a year worth of recordings. It's a 16-channel system with 400 hertz sampling frequency. And in total with our dogs, we had over 1,500 days and 348 seizures available. We also used a couple of patients from Mayo's epilepsy monitoring unit, intracranial patients. We had a pool of 120 patients to choose from, and of course the electrode configurations varied widely. These were all wide bandwidth patients, 5 kilohertz, and in total we had over 500 days and 942 seizures to choose from. And of course with the patients, the real challenge is seizure clustering, is looking for lead seizures. Again, patients are in the epilepsy monitoring unit for maybe up to 10 days in most cases. If we enforced a 4-hour separation between lead seizures, and it's just difficult to find patients that have seizures at exactly the right spacing, enough seizures to really fit this model well. And I think most of you are familiar with this. I'll go over it rather quickly, but this is the NeuroVista system that was used with our dogs. 2 bilateral 4-contact strips, one on each hemisphere, or 1 pair on each hemisphere. They're connected to this implantable telemetry unit, which the wires tunnel through the dog's neck, and it's implanted under the latissimus dorsi muscle. Wirelessly transmits the data to this personal advisory device, which has a little slot for an SD card in it, and that's basically we have a technician pulling these SD cards out every few days, every week, and then uploading them to a cloud-based storage system. The contest that we ran went from August 25th of last year to November 17th. It was timed to coincide with the American Epilepsy Society annual meeting. They were kind of the main sponsor of this contest. We ended up using five of the dog recordings. Actually, we had, of our pool of 8, 3 of the dogs had too few seizures. 2 of them were seizure-free after implantation, unfortunately. But 5 of them had excellent recordings and excellent data. We found 2 human 5 kilohertz recordings that worked well and had a good number of seizures with adequate spacing. In order to accommodate the Kaggle format, we split the data up into 10-minute clips spanning the hour before seizures. before the seizure, and I'll talk more about that in a minute. We provided training data from basically the first half of each recording, labeled ictal, preictal, and then the test data from roughly the second half of each data recording in a random order, and of course unlabeled. Lead seizures, as I mentioned, were enforced with a 4-hour separation. And just to be sure, absolutely sure that we had truly interictal data, we restricted ourselves to only pull from segments that were at least 7 days from any seizure, plus or minus. This ended up with 60 gigabytes of data in MATLAB format, .mat files, that were hosted on the Kaggle site and downloaded by competitors. And usually Kaggle enforces a limit of 10 gigabytes on their data contest. So we definitely stretched their capabilities a bit with this competition. All right, and just a little bit more about the data and how we clipped it up. This is just a data segment from one of our dogs. You can see the seizure highlighted in red right over here. If we stretch or compress the time scale, so we're looking at an hour of data. We enforced and this little red blip here is the seizure that I just showed you, just compressed down. We enforced a 5-minute offset from the start of the seizure, just to make sure that we didn't have any early ictal data bleeding over into the preictal period that might bias the results. We chopped the hour up into 10-minute segments, and we also had a 10-second dropout between each segment to prevent competitors from sort of restitching the data. We also used mean normalization on each segment independently for that same reason. And of course, we took data clips from before the seizure into the preictal group, and then interictal clips at a second group. The results, so in total there were $25,000 in prizes, 654 players, which comprised 505 teams, participated, grand total of nearly 18,000 entries, and the top area under the ROC curve was almost 0.84 at the end of the competition. And I don't think I talked about the private leaderboard versus the public leaderboard. The public leaderboard on Kaggle is what gives participants the immediate feedback, but that's only scored on 40% of the data. And the idea is to limit overtraining to the training set, or to limit overtraining and make sure that the solution is extensible to new data. So 60% of the data in this case was hidden. So when the contest was over, that determined the final winners. And this is just a plot over the course of the contest of the top area under the curve on the private leaderboard. The results, these are the top 10 finishing teams, and QMSDP, you'll hear a bit more about that in the next talk, but this was a group that was sort of assembled during the competition across 2 continents and used a very innovative approach. And you notice there are a couple of things. First of all, there was quite a bit of difference between the public leaderboard score and the private leaderboard score. And in fact, these ranks shuffled quite a bit on the last day of the competition. I think some folks were very happy and some were not so much. Also, one thing that we wondered about in running this competition, Kaggle limits the number of submissions that a team can make in a day. We wondered if this would correlate with anything, with any type of overtraining. Were people who submitted more maybe more likely to be sort of overtraining on the public leaderboard? But really, in the top 10, the number of submissions were all over the place. The number 1 team, of course, had 500, but I mean, down here, the number 10 team, and this is again 500 teams, so that's, being number 10 is not too shabby. Only 97 submissions. So, so I think we would tend to conclude that was not the case. That teams that submitted more didn't seem to overtrain more. All right, so I'm running through this very fast, and just to wrap up, this is I think was a very positive algorithm development program here, but there are some limitations we have to just acknowledge. First of all, the data size is always a limitation. Anytime you're downloading data, we weren't able to get the 10,000 to 1 ratio or anywhere close to it in our data. So we still underrepresented that. The competitors get to see the test data. That's kind of inevitable in the Kaggle format, but it does allow them to do some normalization. And if you think about how or in the real world, how a device is going to work, it's sort of future information that we're giving them in a way. So we wondered how that would play out. On the flip side of that, because we had to give them these data clips, they couldn't do any baseline normalization. So we couldn't give them timing information for obvious reasons in the testing set. A lot of algorithms would use some sort of baseline correction, and that just wasn't available to the contestants. Then we wondered, even with this 40-60 split between the public and private leaderboards, are we still overtraining a little bit to that public leaderboard? So following the competition, we invited the 10 best performing teams to participate in a Heldout data challenge. We assembled 5,000 new data clips from dogs 1 through 4. We didn't have any more data on the patients nor on dog 5. And these were both preictal and interictal clips, weighted a little more heavily towards interictal to try to get a little closer to the real world case. And participants agreed to train algorithms only on the original contest training data. And they actually didn't have the answer key for the testing data until after this was done. And we asked them not to make any changes to their algorithms. And the results were kind of interesting. We did find a bit of overtraining, but on average, it wasn't that much. The mean of all these, we had 6 participants, it was just a decline of about 6.5%. When we ran on this Heldout data. So that's really pretty good. It's interesting, the third place team had quite a drop in their performance, and they actually went back and worked through their code and found a few bugs and resubmitted another entry with some better results on the Heldout data. But of course, that wasn't really part of this experiment. So just in conclusion, I think this highlights the power of sharing data and algorithms, and this is all available on IEG.org, our dog data. Using this direct head-to-head comparison really does help accelerate the science and makes research a little more reproducible, because anybody can go out and benchmark against these different algorithms. The fact that 10 different competitors using very different approaches were able to successfully identify preictal periods with better than 0.8 area under the curve seems like pretty strong evidence that seizures are forecastable. And I guess in conclusion, in the contest format, we'd say the contest seems to be fairly efficient at algorithm exploration, that type of development. And the overtraining that we see is fairly modest and seems manageable. And just a quick word about the continuing work with our dogs. We've actually just implanted a beagle with epilepsy in June, the Medtronic RC+S. So in terms of Heldout data, I guess this is sort of the ultimate form of Heldout data. It's streaming off the dog right now as we speak, and we hope to try these algorithms on this data as well. Lots of acknowledgments. The contest sponsors, the AES, the Epilepsy Foundation of America, NIH, and Kaggle.com waived part of their normal fee, so they contributed quite a bit. Ned Patterson and Charles Veet from University of Minnesota and University of Pennsylvania did a lot of the data collection, and that's really hard work, so they deserve a lot of credit. And the Kaggle.com team and the IEG portal team all were instrumental in this. And this is our research group and collaborators. I think I'm out of time, but just want to give due credit to all the support and from our collaborators and from our lab.
available for the contestants after they submit it? Can they use it in their future publications to develop any future algorithms?
Absolutely. The actual data clips that we use are still downloadable from Kaggle, and then the full records, the continuous time records, unclipped, unexcerpted, are available on IEEG.org. Yeah, we encourage people to go out and work with the data to continue developing their algorithms. On the forums, there were quite a few contestants who seemed interested in that. And
Ben, I just, wanted to congratulate you and your team on this. I mean, I remember when this organization started in 2001, and people were debating whether you could even predict or anticipate seizures and whether seizure generation had something to control warning at end. And we didn't really know exactly what the goal of the group was at that time, but this was it. And I think the organization, has moved way beyond this and branched into all sorts of basic science things and all that. But there were wild claims by a variety of groups for many years that turned out to have flaws that we all worked through together. But this is what we were trying to achieve, and it's amazing that 14 years later, it's been done. It's not finished, it's not clinically fully applicable. But I think we should all take at least a second to kind of savor the fact that together, by collecting the right data set, by getting people in industry to help build a device that can do it, that by finding a way to engage the scientific community, 500 teams worldwide, that together we accomplish something. And I think, we're working on these papers now. I know you're working on your paper. But one of the things that paper has to say is that this organization really accomplished something.
yeah, absolutely.
Any other questions or comments?
Yeah, I also want to congratulate you to that work. I downloaded also data and found a little bit pity that there was a time shuffling. So sometimes I would like to look at the evolution over longer time spans than just 10 minutes of some feature in the EEG.
Absolutely.
I do not know how you can really get better solution.
Yeah, absolutely. That's available. We can talk about how to get that to you. But yes, absolutely, that's available on the portal. I'm sorry.
Okay, please join me thanking Benjamin again.